Okay, so this is question number 2 in section 7, and it's the reaction between solid carbon and carbon dioxide gas, giving you 2 moles of carbon monoxide. And part of the reason why they give you an equation like this is it's easy to make a mistake and confuse carbon dioxide and carbon monoxide, right? So that's probably part of the reason. Anyway, so you have a temperature of 1160 Kelvin, you have 2 liters volume, and the total pressures in the container are here on this table. So first you have to write the equilibrium constant, the expression for this reaction. Remember, the solid has nothing to do with this Kp, so we would write the partial pressure of the products squared divided by the partial pressure of the gaseous reactant here. Sorry, that's a little messy. Okay, so that would be the equilibrium expression. And again, you put the P there if it's gases and pressure. So B is calculate the number of moles initially placed in the container, assuming that the volume of the solid is negligible. So because at time 0, we have a pressure of 5, that is entirely the partial pressure of CO2. So we have 5 atm, we have a temperature of 1160, we have a volume of 2.0 liters. So of course we would use PV equals nRT to determine the number of moles. And I did that on a separate piece of paper so that I had it. And the answer that I got was 0.105 moles, 3 sig figs of CO2 gas. Okay, now for the reaction mixture at equilibrium, the partial pressure is 1.6 atm. So calculate. So there's 2 ways you can do this. You can do it an easier way or a harder way, but the harder way is great practice. It's not harder, it's just more involved. So if you could see that if you have 8.37 at equilibrium, that's your total pressure. If they told you the total pressure of CO2 is 1.63, the remainder would have to be the carbon monoxide. So you could do something like 8.37, and I would do this if it makes sense to you, minus 1.63. And then when you do that, you get 6.74 atm. So that has to be the pressure of the CO. Another way you can do it is just to verify kind of like the ICE method. So if I just look at the reaction, carbon solid plus CO2 gas gives me 2CO. I can do an ICE table, right? Which is always a good thing to do because there's definitely going to be on the exam anyway. So your initial pressure of, carbon dioxide is 5. We don't care about a solid. Our initial pressure is 0. Our change is minus x. Our change is plus 2x. They told us that the partial pressure of carbon dioxide at equilibrium is 1.63. And then here we would have 2x. So if we just solve for x, so 5.00 minus x equals 1.63, we would end up with an x of 3.37. So our answer, right, so at equilibrium, our partial pressure of CO2 would be 1.67. Our partial pressure of CO at equilibrium would be 2 times 3.37, which is 6.74. So it gives you the same answer, but it's just kind of interesting to look at it in both ways. Okay, and then just calculating the equilibrium constant value, you would plug in those numbers. So I'm just going to go back up here. Maybe I'll use blue. So my partial pressure of CO is 6.74. And again, I'm squaring that, divided by the partial pressure of my CO2, which is 1.63. And then when I crunch the numbers, I end up with 27.9. So let me just erase all of this stuff here. So if I have 27.9 as my equilibrium constant, that means I am favoring my products, right? So I'm going to have more products than reactants at equilibrium because my Kp is greater than 1. So D says if a suitable solid catalyst were placed in the reaction vessel, so solid, would the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final pressure? Justify your answer. Okay, so because a catalyst does not affect equilibrium concentrations, right? The only thing a catalyst does is it affects the speed of reaction. So if you wrote, although the reaction is going to occur faster with a catalyst, it is not going to affect the equilibrium concentration. So therefore, the pressures at equilibrium are going to be equal without a catalyst or with a catalyst. Okay, in another experiment involving the same reaction, we have the same volume here, 2 liters, 10 grams, whoops. And then we have each of them at a partial pressure of 2 atmosphere and same temperature. So if they're at the same temperature and same pressure and same volume, they're going to have the same number of moles. So looking at the equilibrium constant right here, because it's large, you're going to have more CO. So if you're going to have more CO, if they're starting out at the same, the reaction is going to shift to the right to try to make more products. So as a result, the partial pressure of CO2 will decrease. So again, you could do a calculation with that. You could do a Q, right? So I was just talking about that, qualitatively, but quantitatively, you could do a Q. So you could say, all right, so I have 2 ATM of my product. I have 2 ATM of my reactant, so I have 4 over 2. My Q is equal to 2. So because Q is less than Kp, the reaction is going to proceed to making more products.